Welcome back, guys, and I do hope as ever you and your family are keeping well. So what we're going to look at today, and we're getting close to ending our topic on electric fields, is electrical potential energy. So what we're going to look at in this video is electrical potential energy. That's the work you need to do, the energy you need to provide to move similar point charges closer together. Now, it's not particularly easy, but if you remember the work you might have done on gravitational fields, I think you'll see the similarities with this topic. So let's kick off by considering 2 point charges. So I'm going to draw a charge here, and I agree that's a little bit bigger than a point, but you've got to be able to see it. And I'll draw another charge here. And you'll notice that these charges have the same sign. They don't need to be the same magnitude. They can just be a Q1 and a Q2, or a large Q and a little q. But the important thing is that those charges are separated by a distance. So we'll go from the center of this one to the center of this one, and we'll indicate that separation with the letter R. So I'm just going to remind ourselves that we should consider these to be point charges. Okay, and what we're going to do with these two is we're going to push them together. So we're going to apply a force that pushes the charges together. In other words, reduces R. Okay, now the important thing here is, because these are similar signs of charge, they may be different values of charge, so you've got to be a bit careful when you say similar charges. What you mean is the magnitude of charge on each could be different, but they're both positive. When we push them together, we're going to have to overcome the electric field of each one, the Coulomb repulsion. And as we push them closer and closer together, you might remember that those field lines get closer together, so the force you have to apply gets bigger and bigger. So it's not just a simple sort of GCSE calculation of saying that the energy we need to provide or the work we need to do is just force times distance, because the force isn't constant. But what we do know is when we push them together, we will do work. We will put energy into the system, and that will be stored as electrical potential energy. And then when we let go, they'll fly apart and release that electrical potential energy as kinetic energy. So we know from GCSE that the work we do will be the force times the distance we move that force through. The problem is, of course, that the force that we apply is going to get larger and larger and larger, because the electric field gets stronger as we get closer. I didn't want to go off on one with gravity, but you might remember the work that we did with gravitational fields, that we can use FD, simple formula, if we're on the Earth's surface, because the gravitational field is uniform, so G stays the same as 9.81 newtons per kilogram. But when we move out to orbits and we look at planets orbiting and things like that, we can't use simple formulae like this, because the force of gravity gets weaker as we move away from a large mass. So we're going to see a similar sort of thing when we deal with point charges. So how are we going to work out the energy that we need to feed in to get these charges to a separation R? Well, the first thing we need to take into account is, let's find a point where they've got no energy at all. Now, you might remember this with gravitational fields, that we introduced the idea of what's going on at infinity. Don't overthink this one, okay? It's very difficult to imagine, how can I put 2 point charges at a distance that's infinitely far apart? But just consider that R is so massive that they don't feel forces due to each other. Consider that to be infinity. And then as you move them closer and closer together, they'll begin to feel each other's forces, And as you get closer and closer and closer, the force you need will get larger and larger because the electric fields are getting stronger. So what we're going to do now is look at this graphically. So again, you'll see the similarity here with gravitational fields. So I'm going to draw a set of axes. So here we go. Here's the y-axis. And here's the x-axis. And the y-axis is going to be the force that we need to overcome at any point when we're pushing these things together. And this is going to be the separation of the charges. Okay, now that sort of complicated idea of infinity, let's have them separated by a very, very, very large distance. In other words, they're separated by an infinitely large distance. So over here is going to be infinity. Now, as we push them closer together to get them to separation R, we're going to have to push harder and harder and harder. And therefore, for every meter that we move closer, we're going to have to do more work. So I'm going to come around this side and draw on the graph. So out here at infinity, we can imagine the force tends to 0. And then the force gets bigger and bigger and bigger and bigger as we push them closer and closer together, and it continues asymptotically. Here we go. Try and draw a slightly better line. Okay, so we were out at infinity, and we're going to push these things closer and closer together, and let's get them to separation R. So whenever we do graphs at A-level or GCSE, I always say to students, look at the axes first. What are they measuring? What does it tell you? Okay, what's the force between these two that we have to overcome at different distances between the point charges? Right. Then look at the units, okay, and be really careful at the multiplier. Could this be in kilonewtons? Could this be in millimeters? Okay, which would catch you out. When you've done that, I always suggest you look at the gradient, which we won't deal with yet. And I always suggest you look at what the area represents, if it represents something. So take a little square on this graph, just one little square. It's a measure of force times distance. Work done, energy transferred. So the area under this graph is the work that you're going to have to do to move these closer together. So if we get them to separation R, there we go, and we were out here, this area here represents the work done by us, if they're both positive, in moving these two from infinitely far apart to a separation of R. So this is the work done, and it's important where it's from. It's going from infinity to R. Now, the shape of the graph shouldn't surprise you. I hope you remember that with these kind of fields, the force between the two charges is proportional to 1 over their separation squared. So that explains the shape of the graph. So let's quickly summarise that one. We've got 2 point charges that are the same charge, so we are going to have to do work, and when we get to there, we will be storing the energy as electrical potential energy. And as we let go, they'll fly apart and they'll release their energy as kinetic energy. Now you might say, well, hang on, how does this work for something that's a positive charge and a negative charge? Well, think about it in exactly the same way, but what you're going to have to do there is you're going to have to do work to separate them. Okay, so they'll be close together, yeah, with a very, very low amount of energy, and you will have to do work against the attraction. In other words, you're feeding in energy, and they will be gaining. You can almost imagine it like stretching an elastic band or a spring, though it's not the same mathematically, that as you pull apart a positive and a negative charge, you're feeding in energy, you're doing work, and that work is going into electrical potential energy. And then theoretically, if you pull them apart to a far separation and let go, they would attract each other, and you get that energy back as kinetic energy. So the physics is the same either way around. Just think of which way you're having to apply your force to do work on the system. So let's now look at how we would calculate this area under the force separation graph. And you've got all the maths you need to do this already. So you know the force between any 2 point charges is equal to 1 over 4 pi epsilon naught. The first charge, which we'll call big Q, the second charge, little q, over r squared. And you've heard me go on and on about this. You need to be sort of flexible with this. It's not necessarily a large amount of charge and a little charge, though it could be. It's just a Q1 and a Q2. Okay, and it doesn't matter what order they're in, of course. So if that's the force, what happens if we multiply it by the distance? Well, at university, you'll look at how you can integrate under that curve. But I'll do it a little bit more simply. I'll just say let's take an r out of here and have force times by distance. Well, that's going to be equal to our constant, which has dimensions, 1 over 4 pi epsilon naught. I'm sure I've said this a million times, but I think most A-level exams give epsilon naught, which is really annoying. They don't give you 1 over 4 pi epsilon naught, so you need to work that out. Q over R. Okay. So this is the work we have to do in moving the two charges from infinity to a separation of R. So it's the work done, it's the energy transferred. So the energy, be really careful with this E, I'm going to come back to that in a minute, is equal to 1 over 4 pi epsilon naught Q1 or Q, Q2, little q, over R. So we now have a formula for the amount of work that we will have to do in getting those two charges from infinity to a separation R. Now, this E here, this is so complicated because we're doing E electric fields, etc. Look at the formula and then ask yourself, what is this E? Yeah, this is energy. Okay, this is the work that we've had to do. So it's really important that you are aware that this is not anything to do with electric field strength or something like that. Okay, so this is the electrical potential energy. And you can think of that in two ways. It's the work that we've had to do to get the two positive charges closer together, or it's the electrical potential energy therefore stored in the system at separation R. So just before we do a quick example, there's something I'd just like to note, and I think you've got the hang of this, but it's worth mentioning. The difference between pushing together two positive or two negative charges and what happens when we do a similar thing with opposite charges. So here's a positive charge and here's another positive charge. Okay, and if we push those together, we're increasing the electrical potential energy. So E is positive. They've sort of got electrical potential energy and more of it as we push them together. But what happens when we've got this arrangement? So there's a negative charge, and there's our positive charge. So in this case, when they're close together, you can imagine them as sort of not having electrical potential energy. They're short of electrical potential energy. So in this situation, we can say that you need to feed electrical potential energy into them to pull them apart. In other words, when you let go, they'll get more and more kinetic energy and they'll lose electrical potential energy. So we can say that E is negative. Now, I'm going to do a quick example on this in a second, but what I'd like you to do is, having done this, just to think, well, what about this for an example? Think about chemical situations and think about breaking bonds. So, bonds in structures, molecular structures or atomic structures, are forces between charged particles. And if you think about it, this sort of situation suggests that the bond will form, that they'll be held together and they'll be short of energy, short of electrical potential energy. And what you'll need to do is to do work to pull those apart, to break that bond. And it's that I want to look at next. So let's end this video by doing a quick example. And there's going to be a few assumptions here, but it's about getting the idea. So I'm going to look at the bond in salt, and I'm going to look at one atom of sodium and one atom of chlorine bonded together. So let's have our sodium atom, and that's positive in the ionic structure. Okay, so we're going to give this a charge. Well, if it's a 1 plus, it's going to be charged exactly E. I'll put plus E just to remind us it's a positive charge, but E is the fundamental charge, the charge on a proton. And that's bonded. I'll just draw a bond there. I'm not sure the chemists would be happy with what I'm doing, but you get the idea. To the chlorine. And the chlorine in this structure will be negative, and it will have a negative charge of minus E. In other words, the charge on one electron. Okay, so that means that the sodium chloride, a single sodium chloride, two atoms bonded together, will be neutral. So what we can imagine, and again, I'm not drawing atomic sizes correctly here, but we can imagine we've got the sodium particle, okay, bonded tightly to the chlorine. You can see the sort of assumptions I'm making here, okay. But what's important for us when we look at the energy we need to feed in to break this bond is how far apart are they? So we'll imagine they're point charges. There's the middle of the sodium. There's the middle of the chlorine. And we've got a sort of bond length here, which will be their separation. And I looked this up and you get slightly different values. But the bond length depends on quite a lot of things. We'll make it equal to 0.24 nanometers. Okay, so in many ways that's not far off the diameter of an atom, which sort of makes sense. Okay, this mark here should be right in the middle of the chlorine. I haven't quite got it in the center of the chlorine, but you get my idea. Okay, so let's use what we've got here to see if we can work out how much energy we need to feed in to break that bond. Now, I don't want to get into the details of the chemistry here. Obviously, the bond is broken if they're moved a small distance apart. The structure will fall apart. But what I'm really implying here is so they do not interact with each other at all. In other words, we're going to have to move these two to a separation that is infinitely far apart. So let's get started on this calculation then. I've made my R look a bit better now. In other words, from the centre of the sodium atom to the centre of the chlorine atom. So what do we know? Well, we know from the work we've just done that the energy we'll need to feed in will be equal to 1 over 4 pi epsilon naught. That's just the constant. Q upon, be careful, R. Okay. And again, it doesn't matter which way round the charges are, but we could make that the sodium and we can make that the chlorine. Okay, so let's put some numbers into this. So E, the energy we will need to feed in to get them, okay, from R to infinity. You might think, well, hang on, isn't this the energy that they sort of have at the moment? I can sort of take your point, but if they came from infinity to there, okay, they will have come rushing in with kinetic energy. We're now going to have to feed in the same amount of energy to get them back to infinity. And again, it's one of those things that you should understand physics, but don't overthink it, or you get in a real tangle about where's infinity and what's going on. Okay, so 1 over 4 pi epsilon naught, and then Q over R. So I'll write these numbers first. So isn't that 1.6 times 10 to the minus 19? And that is 1.6 times 10 to the minus 19. Okay, but this one is negative. So we've got 1.6 times 10 to the minus 19. Okay. Squared, because we've got a Q and a Q, that's the two of them, divided by their separation, so nanometers, 0.24 times 10 to the minus 9. Okay, so this 1 over 4 pi epsilon naught, okay, I should have actually put the numbers in there, but that's going to be 1 over 4 pi, yep, and then epsilon naught, 8.85 times 10 to the minus 12. Okay, and if you bash all of that out on your calculator, and I strongly recommend you do a stage at a time and save that, rather than put the whole lot on the screen, because you could make a mistake. Okay, the energy that we will need to feed in to pull these apart comes out at about 9.59 times 10 to the minus 19 joules. Okay, a very, very small amount of energy, but think about what that small amount of energy means on an atomic scale. Now, I thought it might be interesting to calculate how much energy this is in electron volts, because it's good revision, but also electron volts give us sort of numbers that are kind of easier for us as humans to understand, because it gets rid of these very, very, very small powers of 10. But before we do, there's something interesting here, and probably physicists a little bit better than me are probably shouting at the screen now, going, FJ, you've made a mistake. Well, I haven't made a mistake. I want to make a teaching point. Remember that this E here is the electrical potential energy in the system at separation R. And I've spent all my time saying that if one's positive and one's negative, they're close together, so they're lacking electrical potential energy. So to make that point in physics and to be really consistent, that's positive, that's negative, and if you multiply a positive number by a negative number, you get a negative number. So this squaring here is just my way of doing Q times Q. It's not something where we've got a negative number squared. So there will be a minus sign in front of this. And therefore, to be consistent, probably less important in your A-level, but to be consistent, the answer will be a negative value because this is the electrical potential energy that these two have not got. It's the electrical potential energy that they lost in falling in from infinity. They're short of electrical potential energy, and it's that we have to put back into the system by pulling them apart and breaking the bond. So finally, let's work this out in EV. So we'll stay with purple, shall we? So what have we got? We've got 9.59 times 10 to the minus 19 joules. Let's be consistent now and say that's the electrical potential energy we're short of. To convert to joules, okay, you want to make the number that you write down appear bigger. That's really bad maths, but I'm going to say that again. That what the answer should appear as 1, 2, 3, 4, 5, or 100, or 1,000, or 1,000,000. You're trying to get rid of this, okay? So if your answer comes out as something times 10 to the minus 20, or minus 19, or whatever, you know you're wrong, okay? So divide by the fundamental charge, 1.60 times 10 to the minus 19, and that all comes out at about minus 6, I'm just going to put it down as 6 electron volts. Okay, and finally, because I've absolutely got to do this, yep, this negative symbol here is the energy it is short of to fall apart. I'm sure it's not the first time you've seen that, but you can see why we talk about bond energies in this case as being negative, because a bond is a low energy situation. It's sort of down a potential well. We've got to feed energy in to get the particles out and further apart. Good, so I hope you found that video useful and you've got a good understanding now of electrical potential energy. We're on the home straight. I've got one more film to make and we're going to look there at electrical potential, not to be confused with potential energy, and we're going to have a brief look at equipotentials. So I'll go and make that video now and I look forward to seeing you next time.